Welcome back, focused learners. Today we're jumping right into a really fascinating chapter from the Ganita Prakash curriculum. It's called Playing with Constructions. In this explainer, we're basically going to transform from passive readers into active architects. We'll be unpacking the foundational tools of geometry to see how just a few simple rules can help us construct incredibly precise shapes. So get ready to rethink the basic geometry you thought you knew, because we are getting hands-on today with the Architect's Toolkit.
All right, let's kick things off with a big question. Take a look at this intricate artwork. Do you think you could draw this complex sun pattern with all its perfect curves and spiraling center using literally nothing but a ruler and a compass? Well, our chapter challenges us to do exactly that. The goal is to try drawing these figures freehand first and then suddenly realize the absolute power of using the right instruments.
Let's jump into Section 1, the magic of curves and mastering the compass.
So go ahead and arm yourself with a compass. It's a pretty simple mechanism, right? Just one sharp, fixed metal point and a moving arm holding a pencil. But hey, don't let its simplicity fool you. This seemingly basic school supply is actually an instrument of incredible discovery. It allows us to perfectly replicate distances and sweep through space with absolute mathematical precision.
Now, here's a really fascinating redefinition of a word we use every single day, a curve. In standard conversation, a curve implies something that bends. But in the mathematical language of this chapter, a curve is defined as literally any shape that can be drawn on paper with a pencil. That means circles, swirling waves, and yes, even perfectly straight lines are officially categorized as curves. Pretty wild, right?
Moving right along to Section 2, Anatomy of a Circle.
Our text poses this brilliant thought experiment. Imagine placing a single point, let's just call it point P, on your paper. Now try to hunt down and mark every single spot in every possible direction that is exactly 4 centimeters away from point P. If you marked 10 points, 100 points, or even an infinite number of points, what shape naturally emerges on the page?
Well, instead of just guessing, the chapter gives us the exact steps to construct this reality. First, mark your point P. Second, open your compass so the distance between the needle and the pencil is exactly 4 centimeters. And finally, and this is the golden rule of construction, keep the metal point firmly fixed on P and smoothly move only the pencil. By following these 3 simple steps, the shape that perfectly reveals itself is a flawless circle.
So, the absolutely crucial takeaway here is that this construction completely defines the anatomy of a circle for us. That fixed point, point P, where our compass needle stood its ground, that is officially the center of our circle. And that strict 4 centimeter rule we followed, the constant distance from the center to any point on the outer curve, that's what we call the radius. Every single point on that drawn curve is exactly the radius distance away from the center.
And this brilliantly illustrates how we can take that basic circle and really start playing with it. Check out these intricate waves. We aren't just drawing full circles anymore, we're drawing half circles along a straight central line. By alternating the placement of the compass point along that center line and keeping a consistent radius, chaining together those perfectly measured half circles creates this intricate flowing artwork. The source even challenges us to make the waves smaller or larger by adjusting just that one parameter, the radius.
Okay, let's shift gears a bit. Section 3, Rectangles and Squares.
Here, the chapter asks us to define what actually makes a rectangle and a square. When we compare them side by side, they've got some striking similarities. Both shapes demand that all of their interior corners are perfect 90-degree right angles. But notice the key difference in their boundaries. The square is super rigid. It demands that all 4 of its sides be exactly equal in length. The rectangle, however, is a bit more relaxed. It only requires its opposite sides, the ones facing each other, to be equal.
Now, the text doesn't just want us to passively read these rules, it wants us to test them out. So I challenge you to grab your ruler and try drawing this right now. A rectangle with sides of 2 centimeters and 10 centimeters. It forces you to construct a very long, thin shape, proving that as long as those opposite sides match and the corners are exactly 90 degrees, the laws of the rectangle hold perfectly true no matter how stretched out it might look.
Let's dive into Section 4, Discovering Diagonals.
The chapter now introduces us to a brand new element, the diagonal. If you take a rectangle, say with corners P, Q, R, and S, and you draw a straight line from one corner to the complete opposite corner, like joining P to R, you create a diagonal. You're essentially cutting that geometric room right in half.
But what happens when you draw both diagonals inside a single rectangle?
Well, they cross right in the middle. Suddenly, our simple four-sided shape becomes this complex intersection. Just notice what happens when we chart this out. By crossing two diagonals, we instantly have 8 internal angles to measure around that center point. The text highly encourages us to construct this, measure the actual lengths of the two diagonals, and measure those 8 angles to discover some really cool hidden symmetries.
You know, to truly play with constructions like a mathematician, you really need to observe patterns. The text asks us to track a few general laws. What happens to the lengths of those diagonals? Are they equal? What about those 8 interior angles? Which ones actually match? And most importantly, what happens to all these measurements in the special case of a square? When a standard rectangle magically transforms into a perfect square where all sides are equal, how do those crossing diagonals change?
Finally, the chapter leaves us with this provocative puzzle to really test out your newfound architect skills. We know a square has 4 equal sides and 90-degree angles, right? But is there a four-sided figure out there where all the sides are perfectly equal in length, but it is not a square? If such a shape does exist, how would you use your trusty ruler and compass to actually construct it? I'm going to leave you to ponder that geometric mystery. Keep your tools sharp, keep experimenting with those curves and lines, and I'll catch you in the next explainer.